Okay, polarity and solubility. So first, a couple definitions. Hydrophobic, right? Water fearing. So hydro for water, phobic means fearing. So hydrophobic is something, a repulsive interaction between a solute and water that diminishes water solubility. So if something's hydrophobic, it doesn't want to be dissolved in water. Okay? You might be able to dissolve a tiny little bit of it in water, but not a whole lot. So hydrophilic is water loving. So this is an attractive interaction between a solute and water, and that enhances water solubility. Okay? So things that are hydrophilic are readily dissolved in water. And as you might guess, hydrophobic and hydrophilic can be connected to the intermolecular forces present in a molecule. Okay? And so last thing, Amphiphile. Amphiphile. So that is a molecule that contains both hydrophobic and hydrophilic groups. Okay? So for example, here's a long chain alcohol molecule. Actually, there's two of them. Okay? Two long chain molecules interacting. So I'll note that we have molecule number 1 and molecule number 2. Okay? So as you might guess, things are hydrophilic when they can hydrogen bond, right? When they're polar. They don't have to only hydrogen bond to be hydrophilic, but it's helps a lot. But definitely things that are polar are usually hydrophilic. I'm going to keep recording this. Okay, 1 second. Okay. I might have to go soon. So as you can see with this molecule here, it's got this long chain of just carbon, 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 carbon. Okay? That makes it very much like the octane molecule that we talked about, right? They're these long spaghetti noodles that can kind of get tangled up. But in this particular molecule, in this long chain alcohol, it has this OH group. Okay? So if I were to zoom in on that OH group, that is still very much a tetrahedral oxygen, right? So if I zoom in on that, I'll show you this carbon. So there's 2 hydrogens. That's what this CH2 group looks like. And then there's a bond, and then an oxygen, and then another bond, oxygen. Okay? So it looks a lot like water. And because it looks like water, it's going to interact similarly as water. This long chain right here, this hydrophobic chain, it's nothing at all like water. It's more like grease, right? So these amphiphilic molecules, I'm going to skip a couple slides, they do really well as what we call surfactants. Okay? Or commonly soap. Okay? As it turns out, soap molecules have these nonpolar greasy tails, and these hydrophilic, sometimes even ionized in some particular surfactants, these hydrophilic head groups. And so these work really well as soaps or detergents because this end of the molecule can really get in there and attract to things that are hydrophilic. But this greasy part of the molecule is really good at interacting with grease and non-water soluble things. So when you have a molecule that contains both of those functionalities, it works really well as a detergent or as a soap. Okay? And so where this is connected to solubility, so if we imagine, let's say, a water methanol solution. Okay, we know water looks like this. Okay, methanol, on the other hand, looks like this. So meth being 1 carbon. Okay, so that's what methanol looks like. So methanol is very similar to water. Okay, and in fact, when you're looking at this picture, you know, there's a methanol, there's a methanol. It's almost hard to distinguish them from the water molecules. So they make a homogeneous solution. If you mixed water and methanol, they're both very soluble with each other. Okay, so the result is it makes a homogeneous solution. So if you imagine something like water and octane, on the other hand, octane is not able to hydrogen bond at all to the water. And so because it can't even get in there into that hydrogen bond network, you'll make this heterogeneous mixture. They will actually be separated, okay? For those of you that cook a lot, you might notice, or you might have observed before, when you're making soup and you put the soup in the refrigerator, it separates, the fat layer separates from the water layer, right? Because fat and water makes an endothermic solution. I think we talked about this. Maybe we talked about this. Maybe I'm imagining what we talked about in my physical chemistry class. In any event, you can get fat and water to mix if you apply heat. But as soon as you take that heat away, they separate, okay? So I think that's a pretty good description